That's it, thank you. All right, so I just wrote some definitions that we saw last time, which was a while ago, actually. So one of them was proximality, which is a notion for elements of GL of V, for some finite dimensional space V. We had 3 characterizations. I just wrote 2 because we're going to be focusing on these 2 for now. And the third one will come back later. So essentially, a gap in the first 2 eigenvalues, meaning that the first eigenvalue, the largest eigenvalue, will have multiplicity 1, right? Because when we wrote lambda 1, lambda 2, and so on, it was with multiplicity. And that's the same as having a pair of an attracting point in the projective space and a repelling one in the dual projective space. And the other notion that we saw was that of hyperbolic groups and the action on its boundary. And we'll be using, in some way you can really identify hyperbolic groups from the property of this action, right? That's a famous theorem of Bowditch, saying that if you have an action of gamma on some space satisfying this convergence property and some extra assumption, which is, for example, saying that any pair of points, of distinct points, gamma plus, gamma minus, can be obtained by such a sequence, and then this will be the action of a hyperbolic group on its boundary. Okay, so now we're going to put these 2 notions together. That's the point of today's lectures. By talking about limit maps. Also, I forgot to say last time that I also have lecture notes for this that are on my webpage that are subject to some evolution. All right, so the setting now is that we have a hyperbolic group gamma. And we're studying representations rho of gamma into SL of V. And we're going to start with the definitions of what we call limit maps that have already entered the picture last week. So what we call, sorry, I should say it will always be transverse limit maps. And if I forget the word transverse, well, it should have been there. Okay, so transverse limit maps, it means a pair psi and psi star, where psi, both of these are maps from the boundary of gamma. So psi is a map from the boundary of gamma to the projective space, and psi star, same thing with the dual space. That we will always assume to be continuous and equivariant. Meaning rho equivariant, right? So gamma acts on both the boundary and on the target spaces of these maps by rho, and the natural action on its boundary on the boundary of gamma. And transverse means that for any distinct points, eta plus, eta minus, in the boundary, if you look at psi on one of those and psi star on the other one, these things will have to be transverse, right? So that will be the basic definition, and essentially Anosov representations can always be defined in most of the characterizations as representations of hyperbolic groups admitting transverse limit maps with some extra property. And we're going to see several instances of these properties that will define, that will characterize Anosov representations. So the first property, maybe that was the first item of the definition. The second one would be dynamics preserving. Well, I should be saying that psi and psi star is dynamics preserving. And that will be a notion essentially on the dynamics of individual elements of gamma. So dynamics preserving means that for any infinite order element in the group gamma, rho of gamma will have similar dynamics than that of gamma on its boundary when it acts on the projective space, meaning that rho of gamma is proximal that the attracting point in the projective space, this L plus of rho g, will be psi of gamma plus, right? Because gamma plus is an attracting point for the action on the boundary of gamma, right? Because for hyperbolic groups, if you put these two notions together, when the sequence gamma k is just sequence of the powers gamma k, it's saying that when you let the powers of gamma k act on any one except possibly for this repelling point gamma minus, the action will converge to gamma plus. Right? So really, gamma plus is an attracting point in the boundary of gamma, and gamma minus is a repelling point, and we're asking those to be mapped to an attracting point in the projective space, and the other one to a repelling point, but in the dual projective space. Right, so H minus of rho, those are gammas, by the way. Rho of gamma should be psi star of gamma minus. So this is just dynamics of individual elements. And another notion that we'll see is dynamics of the whole group, meaning any sequence in the group. So we'll call this uniformly dynamics preserving. So that's meaning that if you have any sequence of gamma k's in gamma, admitting limits gamma plus and gamma minus in the boundary, well, then we have some similar convergence, but for the action on the projective space, but except that instead of removing one point, we'll have to remove a hyperplane. Right, so for any L in the projective space, if L is transverse to psi star of gamma minus, then rho of gamma k acting on L will converge to that same point, which is a psi of gamma plus. Right, and then the same. I'll write also the same thing for the action on the dual projective space on the dual. Which is exactly the same, with pluses and minuses in the same places. Just switch the stars and non-stars. Right, and I'll add also that these convergences should be uniform and compact subsets, although this is actually automatic. Right, it is not obvious, but this local uniform convergence is automatic, and also one of these two conditions implies the other, actually. Right, so uniformly dynamics preserving really means that your group has your representation rho. When you let it act on the boundary, on the projective space, it will have really similar dynamics to what you see on the boundary of gamma. And this happens to be a characterization of Anosov representations. So that's the theorem of Kapovich-Lebon-Portier. Which is that rho is projective Anosov, or P1 Anosov. Which I haven't defined yet anyway, if and only if it admits uniformly dynamics preserving transverse limit maps.
Assuming you started with a hyperbolic group.
Yes. I will always assume that I start with a hyperbolic group. I mean, the definition doesn't make any sense because it uses, if it's not, it uses limit maps, right? Yeah, so there are essentially like two families of characterizations of Anosov representations. Those that use limit map to start with in the definition, those that do not involve limit maps in the definition. And those are nice in the sense that they're easy to state. If you're giving a talk and you want to have a definition on the board within 5 minutes, this is definitely what you'll do. But if you want to work with Anosov representations, you'll first have to understand that these other definitions allow you to construct limit maps, because that's what you'll end up using all the time. Right, and since I have several R's, I don't need to have a definition within 5 minutes on the board, so I'm not going to be discussing these other definitions too much. All the definitions we'll use will already have limit maps in the definition. Yeah. So one way that I like to think of this definition here is that it tells you somehow that actually for uniformly dynamics preserving implies that it's dynamics preserving. Maybe I should have said this. Which is something that you can see by applying this property to a sequence which is just the powers of one given element, right? And then you'll use this second characterizations of proximality to find that rho of gamma will have to be proximal, and that psi of gamma plus will be this L plus, and psi star of gamma minus will be this H minus. Okay. But it's telling you that this proximality is somehow happening uniformly for the whole representation, right? By having this for any sequence in your group. But if you want to characterize proximality with the first definition, you could also try to do that uniformly on the group, right? Saying somehow that when you go to infinity in the group, lambda 1 minus lambda 2 should go to infinity. This is not a very reasonable assumption, though, because if you could go to infinity in the group, so like having a sequence that leaves every compact subsets, with a sequence that are all of elements that are all conjugate to each other, that stay in the same conjugacy class. But lambda 1 minus lambda 2 is conjugacy invariant, right? So it's not going to change. So you need to make sure that lambda 1 minus lambda 2 is go to infinity, but only for sequences that are going through infinitely many conjugacy classes, right? And in a hyperbolic group, there are nice ways of stating this. So this will be another definition. So we could say that rho is uniformly proximal. Yeah, this. Apart from dynamics preserving and transverse limit maps, these are notions I'm just making up for the purpose of this course, so you don't have to like them, and that's fine. So uniformly proximal would be that if for any sequence gamma k in your group, and you want to, at the end, have something like rho lambda 1 of rho of gamma k minus lambda 2 of rho of gamma k is going to plus infinity. And what we'll do is ask for, as usual, for gamma k and gamma k inverse to have limits. And to make sure that they go through infinitely many conjugacy classes, we'll ask for these limits to be different. Right, so at least the simple exercise here would be to see that if you have a sequence gamma k with everyone being in the same conjugacy class, then the limit points will be the same.
It's gamma k to the minus 1.
It's, yes, inverse, thank you. Yeah. All right, so you'll often see this condition of having distinct boundary points for gamma k and for the inverse. It's also related to having conical limit points in limit sets and things like this. All right, so your other characterization of Anosov representations here would be something from the work of GGKW. So this is Guerito, Guichard, Cassel-Vinard. Which is that rho is projective Anosov. If and only if it admits dynamics preserving limit maps and is uniformly proximal. So this still uses the, oh, by the way, if you look at the paper, you won't see it in terms of distinct points in the boundary for your limits. You'll see it in terms of stable length going to infinity, which is also a way of making sure that you'll have infinitely many conjugacy classes. Right. And there are also some versions, especially like if you, I'll mention one characterization without assuming boundary maps in the first place, which is a theorem of Cassel and Potry, telling you that actually if you make this uniformly proximal more precise, has some linear, some sublinear estimate in the stable length, then this will automatically imply that it is a projective Anosov. Okay, so now that we have at least some characterizations of Anosov representations, we can go to what we're trying to do, which is the action on this space L in the projective space of V plus V dual, where the pairing is A is positive. Right, so that was what we stated last Friday, that what we're trying to do is, starting with an Anosov representation, construct an open subset of this L on which the group will act properly discontinuously, and such that the quotient flow that we saw will have nice dynamics. Right. There won't be any flow on L for now. I mean, it'll just be briefly mentioned, but not really dynamically. So we'll start with gamma hyperbolic group. and rho, which is projective Anosov. And we'll use this, and especially use the limit maps psi and psi star. Maybe something I could have said also is that these are unique. Like if they're assumed to be dynamics preserving, they will have to be unique. And so this definition will be quite simple. It's the set of productivizations of pairs V alpha such that whenever you take some element eta in the boundary of gamma, you have at least a little bit of transversality between this psi of eta, psi star of eta, and this V alpha. Meaning that either V, the line spanned by V is transverse to the hyperplane psi star of eta, or the line psi of eta is transverse to alpha, right, which is essentially the weakest notion of transversality you can consider between those. Okay, the theorem here. So still Delarue, myself, and Sanders. Would be that first, the easy part, that M rho hat is open. It's invariant under gamma. And it is also invariant under the flow that we saw last time. The second point, which is the important one, is that the action of gamma on this M rho hat is properly discontinuous. And the third point that comes from for free with the second, which is that if gamma is torsion free, this action is also free. So you actually have a quotient manifold and not just an orbifold. All right.
Yeah, I think we're confused about something basic. Does this imply that the points in M rho hat are not in the image of the pair of boundary maps?
No, they could be. But really, the whole thing is that here we're picking the same eta. Right, it's when you pick one point in this sort of limit set, you have this type of transversality, but with the same eta. And what can happen is that V can be psi of something, alpha can be psi of something else, psi star, but of something else, not of the same. And actually, that will be important because that is what will give us the non-Wandering set.
Okay, thanks.
Okay, so first of all, what I should say is that we're not going to spend much time on items 1 and 3 because the fact that 2 implies 3 is pretty straightforward. If you have a properly discontinuous action, you'll have compact stabilizers if they're torsion-free, as finite stabilizers. And if they're torsion-free, then they have to be trivial. Also, for the fact that M rho hat is open, you know, it's an intersection of open sets, maybe not a finite intersection, but a compact intersection, so that's fine, that stays open. Invariance is just the equivariance of your transverse, of your limit maps. And the flow invariance, you know, the flow was just multiplying v by some number and alpha by some other numbers, but since the condition only depends on their classes in the projective spaces, so this is pretty straightforward. All right, so we're going to be working on this second statement, the proper discontinuity. And I'm going to start with a pretty simple lemma, unless there are questions about this statement. No, well, let's get in the proof then. This first lemma will be trying to understand the action of rho not on the projective space, but on the linear space V itself. Okay. So we start with the same kind of statement as always, where we have a sequence gamma k in our group. It converges to some gamma plus in the boundary. The inverses converge to some gamma minus in the boundary. But now instead of having some L in the projective space, we'll have some vector V. And we'll do some uniform, locally uniform convergence right away, so we'll have a sequence in V. So let Vk in V be such that Vk converges to a non-zero vector V. And we're trying to say something about rho of gamma k acting on Vk in the case where V is transverse to psi star of gamma minus. But maybe we can try to see what we already know from what we have on this rho of gamma k acting on Vk, where we can look at the line spanned by this, right? So look at rho of gamma k acting on the line Vk. And this line is converging to the line spanned by V, which is transverse to psi star of gamma minus. Right. So if you look at this definition, which is still on top there, you plug in the class of V instead of L. You'll see that rho of gamma k, well, you put Vk actually, will converge to psi of gamma plus. Sorry? I haven't written it yet. Yeah, that's on purpose. So this is what we already know from this uniformly dynamics preserving limit maps, okay? We know that the line spanned by Vk, when you apply rho of gamma k to it, this will go to this line, psi of gamma plus. So you already know which line is going to, so the only thing you need to know is what is happening to the norm of this vector. Right? And the answer is that it's blowing up. Right. So you could say that this goes to infinity in V as leaves every compact subset. If you'd rather fix a norm and say that the norm goes to plus infinity, that's the same. Okay, but this is some properness argument already. And maybe I could start the proof down there actually. So we're going to look at the proof of this lemma. And we'll break it down into two cases. The first one will be when gamma plus is not gamma minus, when they're distinct. And why is that different? Well, essentially because we're going to decompose all these vectors in different direct sums. So for Vk, what we can do is decompose it as some Vk plus plus Vk minus. where vk plus is in the line which is attracted by gamma k, and vk minus is in the repelling hyperplane for gamma k. So psi star of gamma k minus. And also v will be decomposed as some v plus plus v minus, where v is in the line psi of gamma plus, and v minus in the hyperplane psi of gamma minus. Right. But for this decomposition to even make sense, you need transversality, right? So that's where we're using, for this to be defined, we're using that gamma plus is distinct from gamma minus. And then you actually have some like continuity in Grassmannians or whatever to say that these, if vk is converging to v, then actually vk plus is also converging to v plus, and vk minus is converging to v minus. There's also something non-trivial here, which is that for k large enough, gamma k will have infinite order. So this decomposition of vk also makes sense. If you want all the details, they're in the lecture notes, also in the article. Right, so now what do your conditions mean here? So the assumption on v, the fact that this is transverse to psi of gamma minus, just means that v plus is non-zero. Okay, means that it is not in psi of star of gamma minus. So now we're going to let rho of gamma k act on vk and see where it goes. Well, we're going to decompose this inner vk plus vk minus. But vk plus is in this line psi of gamma k plus, which is this attracting line for gamma k, which is an eigendirection of gamma k. Right? So we can actually replace this first part here. Vk plus is just going to be multiplied by the eigenvalue corresponding to it. So by convention, our lambda i's were some logs, so there's an exponential of lambda 1 of rho of gamma k, and plus or minus in front because the eigenvalue could be negative. That's not a problem. And now this part here, vk plus is converging to v plus, which is non-zero. And these lambda 1s, they're going to infinity. Right? Because lambda 1 minus lambda 2 is going to infinity. That's this uniform proximality. But now that's where we use the fact that we're in SLV and not just GL. Right? Assuming that a representation is in SL tells you that if lambda 1 is bigger than lambda 2, then lambda 1 has to be positive. It can't only have eigenvalues smaller than 1 if it has determinant 1. Right? And this is actually quantitative. So if lambda 1 minus lambda 2 goes to infinity, then lambda 1 goes to infinity. It's a simple computation. Right, so this part here goes to infinity. Its norm goes to infinity. But you have a sum of two vectors. That one could potentially go to infinity too. But since they're transverse, they cannot compensate each other. Right? Right, so this in total will have to go to infinity. Okay? There are several ways of saying that this transversality means that it cannot compensate. What you can do is pick an inner product for which the target things are orthogonal, and you'll see that the sums will need to add in the end, right? So when you sum the norms. Okay, so that's for the case where your limit points are distinct. It's just a matter of decomposing into these direct sums and seeing what happens to vectors. And now you have to do the case where gamma plus and gamma minus are the same point. And that's probably the oldest trick in math. You've done one case, you do the second case, you reduce to the first one. Yes, thank you, equal. Yeah, you've done that already. So the way to do this, there's sort of a standard trick to do this in this whole theory, which is essentially gamma plus equals gamma minus mean that your elements are not regular enough, they're somehow not proximal enough. And there's a standard trick which is combining a result of Abels, Margulis, and Seufer telling you that up to multiplying by a finite number of elements in your group, you can make them regular enough. And then using some other results of Yves Benoit telling you that you can, these norms that you're trying to get here, which are like singular values essentially, are controlled by eigenvalues at the same time. Right? But here you can do something much simpler. And I'm pretty sure there are a lot of instances in this study of Anosov representations. Because the group is hyperbolic, a lot of things are easier. We're just going to change our sequence by considering the element f in gamma such that f of gamma minus, f acting on gamma minus is different from gamma minus. If you're familiar with hyperbolic groups, well, first of all, if you're not familiar with hyperbolic groups, you'll just assume that if I said that we can consider this, then it probably exists. If you are familiar, you'll realize that there are some examples where it cannot exist. But in these examples, a sequence with gamma plus equal gamma minus cannot exist either. So we're fine. And now we're just going to modify our sequence. We'll write delta k, which will be gamma k times f inverse. Wk will be rho of f acting on Vk, and this will converge to something we'll call W, which is rho of f times V. Okay. And now we just have to check that these satisfy everything for the first case, right? So what is delta k converging to? Well, it's gamma k acting on something in gamma. And something in gamma, this f minus, this f inverse, it's not in the boundary of gamma, so it's not gamma minus. So gamma k acting on f minus, f inverse, sorry, is converging to gamma plus, right? And when you look at the inverse of delta k, well, this is f times gamma k inverse. And this is the continuity of the action. And that this converges to f times gamma minus. And by assumption, this is distinct from gamma plus. All right, so we are in the situation where we can just apply the previous case. Well, we have to check that V or W is also satisfy the appropriate condition. And that should be fairly straightforward. All right, if we look at our W, this is rho of f times V. So this is transverse to rho of f acting on psi of gamma minus. That's our hypothesis. And now psi star, sorry. now is where we're going to use the equivariance of these limit maps, that this is psi star of f times gamma minus. Right, so this is the limit of delta k inverse, right? So that's exactly what we wanted. And so the first case can be applied, and it tells us that rho of delta k acting on wk goes to infinity. But this rho of delta k acting on wk, let's replace everyone by their expression. Delta k was gamma k times f inverse, and wk was rho of f acting on vk. So the f inverse and f just compensate, and you're left with exactly what we wanted. So this will also go to infinity. Right. So really, all you need to do is take care of this first case where the limit points are distinct, and then just multiply by one element. And somehow you don't even need the f. You can pick like 2 elements, f1, f2, that will work for any sequence. Like for any sequence, one of these 2 will work, or something like this. Yep.
So for addition representation to straight volume, is this witnessing properness of the action on the invariant domain is the dual domain?
I'm not sure that's exactly the same thing, but it could be. But
like this set in that case is something like points domain. And
yeah, but the fact is that this works for any Anosov.
yeah.
So if you're using some properness which is specific to a Hitchin, then the answer is that no, it's not the same thing.
I'm just trying to anchor it in something.
Okay, yeah, but I don't have the impression that it's the same. I mean, there could be some relation, some one fibering over the other or something, but okay. So let's go back to proper discontinuity now. And once we've set the lemma, we've done most of the work. So what you need to understand when trying to prove proper discontinuity somewhere is often very useful to prove this by contradiction. And by contradiction, that means assuming the existence of a bunch of things. So first of all, you have a sequence, say vk alpha k, converging to some v alpha in M rho hat. So assume there exists all this stuff. The other one would be like a sequence gamma k, which is going to infinity in gamma, so leaving every compact subset or here finite subset, because gamma is discrete. And the condition contradicting proper discontinuity is that you let these gamma k's act on vk alpha k, and this also converges. Okay, so now you need to understand what this convergence means, because you're in this projective space of v plus v dual. So vk alpha k converges to v alpha. This means that the vectors converge to the vectors up to rescaling. So there exists some lambda k's non-zero such that lambda k vk converges to v and lambda k alpha k to alpha. All right. But now, up to replacing vk by lambda k vk, and same for alpha k, you can actually assume that vk converges to v, and same for the alphas. Right, that will be easier to deal with. But what does the second condition mean? The second condition here means exactly the same. This means there exists some other sequence, say mu k, such that mu k rho of gamma k times vk converges to w, and mu k rho of gamma k acting on alpha k converges to beta. But now we can't do that same trick anymore of rescaling a second time, otherwise we're rescaling the first also. So we have to say something about this sequence mu k. So first of all, this convergence here, this rho of gamma k times vk, this is something that looks like the lemma, right? So we want to say that rho of gamma k is going to go to infinity, and then mu k will have to go to 0. And this will be our contradiction. And we'll see how. Let me see, I'm trying to remember how the order is supposed to work with this. I think this is it. All right, so we want to apply our lemma to say that rho of gamma k vk is going to infinity. But for this to work, we have some transversality condition to check. But that's OK, because that's where the definition of m rho hat will be used. So this v alpha is in m rho hat. This tells you that either you pick for eta the gamma minus, and you know that either v is transverse to psi star of gamma minus, or psi of gamma minus is transverse to alpha. Okay. And we're just going to do the first case. And in this first case, we're exactly where we can apply the lemma, right? This v is transverse to psi star, all this stuff. So this lemma tells us that rho of gamma k vk is going to infinity. So now that we have that mu k of rho gamma k vk was converging to some vector w. So if this is going to infinity, the scaling factor has to go to 0. And now to find the contradiction, we're going to use the fact that w in beta is also an m rho hat. Right? Well, actually, we're just going to use the fact that it's in L, meaning that if you look at beta of w, this should be positive. But this beta of w Well, this beta is the limit of mu k rho of gamma k alpha k. Some linear forms apply to some vectors, which are the mu k's, rho of gamma k, vk's. Right, so it's the limit of, you can get your mu k squared out of there. And then you apply rho of gamma k alpha k to rho of gamma k vk. But by definition, this action on the linear form is composing with rho of gamma k inverse. So the gamma k's, they disappear in this formula. This is just alpha k of vk. And now you have one that goes to 0, these mu k's. But these alpha k's, vk's, they cannot go to infinity because they converge to alpha v. Right? Because alpha k goes to alpha, vk goes to v. So now this has to go to 0. So the limit has to be equal to 0, but also be positive, so we have a contradiction. And yeah, so we'll stop the proof here. And I should say also that the other case here is similar. Or you can just say that you apply this first case to the dual representation or something like this. Okay, so are there any questions on this proof? Or? Yep.
I'm not sure that the first assumption is equivalent to not properly discontinuity. So could you?
Yeah, so proper discontinuity, if you write it with sequences, it tells you that if you have a converging sequence and a diverging sequence in the group, then when you apply the sequence in the group, the diverging sequence in the group acting on a converging sequence in the space will have to go into infinity in the space.
I see.
Yeah. And now it's like, if it doesn't go to infinity, then you can extract a subsequence such that it will also converge. Yeah, I'm using this extra step, I guess. Yeah.
So how should one think about M rho hat?
That's a good question. I don't really know exactly. I'll have some. I don't really have examples where I can think of M rho hat really visually. There are some cases where you can do it, and it's in the exercises. One silly case is when V has dimension 2. This L will be the same as T1H2, as the unit tangent bundle of H2, and this M rho hat will be the whole unit tangent bundle, because the condition of transversality will be automatic in dimension 2. There are some other cases where there could be some description of this, but it's one way, but I'm not sure it's that satisfying, is that in general you have lots of literature on the subject of finding domains of proper discontinuity for Anosov representations. Right? Usually they're for actions on flag manifolds. And though it always works with a sort of similar construction, which is you start by finding what are the worst possible points to get proper discontinuity. There'll be some sort of limit set. And then you need to remove, in rank 1 you're used to just removing this, but in higher rank you have to remove something bigger, like what we call a thickening or something. And so by removing not only, I guess, yeah, M rho hat is still there, by removing not only the images of psi star, but something that is transverse to it, we're removing a thickening somehow of this. That's also one way to think about it.
So in general, I know you didn't discuss general simple groups. If the target is a rank 1 group, then we can think of this M rho hat as the unit tangent bundle of the symmetric space.
When we do this in a rank 1 group, yes, it will be exactly that. Yeah. See, I don't have much time yet, but I'll just start with a short introduction to the second part. will be more of an introduction than anything else, which is about this refraction flow. The true goal of the second part will be to introduce the definition of Anosov representations with flows, the original definition. The other goal will be to essentially construct the other part of that we needed to get the nice dynamics on the quotient space, which is we'll construct something which in the end will be the non-rendering sets of the flow on the quotient, right? Yep.
Is this rho hat in some sense unique or maximal or minimal among the?
I think we already had I had the question last time, and then the answer was that I don't know.
Yeah.
Yeah, that's fine. The answer is that I don't know. Yeah.
You didn't learn over the weekend.
Sorry?
And you didn't learn the answer over the weekend.
No. I don't want to know that bad. I do have a feeling like it's in most examples it's kind of maximal. Because what you're removing is like the weakest transversality condition you can think of, essentially. Right? So, yeah. Okay. So we're going to introduce another subset of L from a projective Anosov representation rho, which is the one we mentioned without writing earlier. Pairs V alpha, for which you can find distinct elements in the boundary with V xi of eta plus and alpha xi star of eta minus. Okay. Yes, there exists. Sorry. Yeah, clearly. That would be a really complicated way of defining the empty set. Yeah.
Which has been done before.
Oh yeah, for sure. Okay. And the main result of the second part will be a theorem that we'll attribute to André Sambarino. Which is that the action of gamma on this K rho hat is, well, also properly discontinuous. And co-compact. Yeah.
Proper discontinuity is not automatic.
Yes. So that's a very good remark. That actually, well, why is it automatic? Because there's something that isn't written on the board that you'll want to use to prove this. But given the time, I'll leave it as an exercise. We can. So this is a remark that K rho hat is included in M rho hat. So properly discontinuous just follows from the properly discontinuous action on M rho hat. Okay. So the important part here is co-compact. And that is something quite different. And I don't know, do you have a minute or two? Or okay. I'll just want to discuss the kind of vocabulary that we're going to use in the rest of this part. Which is now we're going to work with flows a lot. The whole point in constructing this is that maybe they should have a definition here also. Now that K rho hat is also invariant under the flow that we had in L, so we have a quotient flow on the quotient K rho. And that's the flow that André Sambarino now calls the refraction flow. At some point, it was called the geodesic flow of rho, and they changed that name, and I'm quite happy with the fact that they changed it. Because I'll be saying stuff that really tells you why you shouldn't be a geodesic flow. Sorry? Is there a reflection flow? Sorry. Of rho. Just the little thing that I want to talk about here is why do we do this whole thing of studying groups and flows at the same time, and what is the relation between those? The main idea is that when you study, say, topological dynamics, for example, or even some ergodic theory, but mostly in topological dynamics, you study properties of flow that don't really depend on the parameterization of the flow, right? You care to know when 2 points are in the same orbit of the flow, but you don't really care about how much time it takes to go from one to the other, right? So when you're studying topological dynamics of a flow, let's say phi t from a space x to itself, the appropriate space, if you want to understand just the orbits of the flow, would be the orbit space, like the quotient of x by the flow. So quotient x by r, where r acts by the flow. But if your x here is compact, which will be our setting, and this flow has any sort of interest in dynamics, this is a very bad space. It will not be Hausdorff, it will not be anything nice, right? So what you do instead is you go to a cover. You lift your flow to a cover so that on this cover, the flow will have a nice orbit space. But now this orbit space will come from an action of the covering group, essentially. So instead, I'll just write a definition that we'll use. Because we'll use this idea, but only for Galois covers, so that's where the groups will appear. So here, just gamma has to be a countable group. It doesn't have to be hyperbolic. What we'll call a gamma flow will be a flow phi t on some space x, where x is a compact, say, metrizable space, something nice. Phi t is a continuous flow without fixed point, as always. And the assumption for a gamma flow is that x is a quotient of another space x hat by an action of gamma, where gamma acts properly, discontinuously, and co-compactly. And the flow phi t lifts to a flow phi t hat, commuting with gamma, but such that this flow phi t hat will have completely trivial dynamics. You've killed the dynamics on this cover. So the resulting action of the flow on x hat is free and proper. And saying that this action is free and proper is saying that now I have a nice orbit space x hat mod the flow. Right? But I've introduced something else in the study of this orbit space, which, if I want to remember that it comes from this flow on x, is that this has an action of gamma on there. Right? And so you have this sort of duality, either working with the flow phi t on this x, which is a quotient of x hat by gamma, or working with the action of gamma on this quotient space here. So what we'll do next time is look at when in the case of hyperbolic groups, we have a good candidate to put here, and we'll try to construct flows for which this is the orbit space with this action. And I'll stop there.
We'll take maybe brief questions, save the long ones for the exercise session. Our camera operator wants to go. Any brief questions?
So, yeah. So perhaps the probably example could be that X had to be the universal cover and gamma to be polynomial X.
Yeah. It's just that for us, like X will not necessarily be a manifold. It could be a pretty fractal thing. But typically, yeah, that would be the case. Takes X a closed surface, and X had the universal cover, and gamma the fundamental group. Yeah.
Next speaker again.